what about the relationships in terms of the strength? Well, in terms of the strength of different types of intermolecular forces there, London dispersion force is the weakest force. Okay. And followed by polar molecules where you have dipole-dipole interaction. And after the dipole-dipole interaction, a special type of intermolecular force, we call them hydrogen bonding, that's stronger. The strongest intermolecular force would be the ion dipole interaction. So this particular table summarizes the relationship in terms of the strength of the intermolecular forces there. London dispersion force being the weakest type, ion dipole interaction being the strongest type. Okay? So we need you to understand the strength of the intermolecular forces among different molecules there. We separate polar molecule from non-polar molecule. Now we would ask you, and we would actually use these different types of, the existence of these different types of intermolecular forces to explain some of the things that we observe. Now, surface tension is one of them. Now, when you have a body of water, on the outside of the water, of that body of water there, a water molecule would actually experience an inward pulling force. Because if this water molecule is right on the edge, okay, having direct contact with the air. Now, there's nothing in the air actually attract the water molecule. However, the water molecules inside the body of water, well, positive end of this molecule will be attracted to the negative end of the other water molecule. As a result, that water molecule on the edge of the body of that body of water will experience that inward pulling force. When you try to pour a liquid out, they tend to form a spherical shape first before the gravity takes over and overcoming the intermolecular forces there, and breaking that water from that drop of water from the body of water. So that is why every time when you pour any liquid out, and if you do it slowly, you will see the formation of a spherical shaped droplet before that droplet breaks up from the main body of water or liquid in that case. So intermolecular forces explains the surface tension there. And then capillary action is another result of the intermolecular forces there. Now you all have this experience there. When you have a piece of paper towel and you dip it in water, water is moving up against the gravity. That's because of the intermolecular forces there between the hydrogen bound of water and the hydroxy group that are present in the cellulose and paper there. So the attraction between H2O and OH group there pulls the water molecule upward. Normally things would just fall down because of gravity, but because of the presence of intermolecular forces there, you see the water moving up against the gravity. Okay? Although minute, that's very important. Otherwise, many of the plants there, they may not be able to absorb the water. Water may not be able to move up there. Intermolecular force is very important there. Okay. Now, another thing that you experience when you do the titration lab, you notice that the liquid inside the burette forms a curved bottom there. We call it meniscus. The reason for that is because in this part, the water molecule does not have much interaction with the glass molecule. But where the water and glass come into contact, there is an interaction between the water molecule and the glass molecule. Holding the water molecules a little bit higher in the middle part, they tend to sag a little bit. Okay, so that's why you have this curved bottom there, and that has something to do, the capillary effect, that has something to do with the intermolecular forces there. So the formation of the meniscus in the liquid, for a liquid in the small glass tubing there, has something to do with the intermolecular forces. Okay, so questions that we can ask you there. Which one is going to have highest boiling point? Nitrogen, oxygen, chlorine, and SiH4. Okay, and in this case, all we need to look at is whether these molecules are polar or non-polar, and also what is their molar mass. And if you look at the molar mass there, all of these molecules are non-polar. How do you know? Well, identical atoms, identical atoms, identical atoms. When you combine them together, identical atoms, they're an En, the difference in electronegatividity equals to 0. So these are pure covalent. Okay. This compound there, tetrahedral structure, silicon belongs to the same group as carbon, carbon group 4A. Okay. So methane has a tetrahedral structure, and this compound also has a tetrahedral structure there. So this molecule is also completely symmetrical. Now, once you determine the polarity of the molecule, the boiling point, these are a group of nonpolar molecules. The boiling point only depends on the size of the molecule. Chlorine happens to be one with the highest molar mass, so chlorine has the highest boiling point. Okay, so these are the things that we need you to be able to answer. Another type of question there, what kind of intermolecular forces do we have? Say for CH3F, fluorine, methyl chloride. Okay, well, we have dipole-dipole interaction. It's a polar compound. But we also have London dispersion force. Remember, London dispersion force occurs in all molecules, exists in all molecules, polar or non-polar. Okay, another type of molecule, ammonia, well, NH3. Well, ammonia is a polar molecule, so there is hydrogen bonding, a special type of dipole-dipole interaction, and also there's London dispersion force. So this is always a part of intermolecular force. Never forget this. No matter whether you have a polar or non-polar molecule, there's always London dispersion force. But depending on the polarity there, you can have dipole interaction, you can have hydrogen bonding. Hydrogen bonding is a special type of dipole-dipole interaction. Okay, so other questions there. We basically, when we try to ask you to answer, when we try to, and when we introduce the intermolecular forces there, we are trying to ask you to be able to use that intermolecular forces to make predictions there based on different types of molecules there. And again, different types of compound there. So we want you to arrange these compounds in increasing order of boiling point. Now here we have an ionic compound. Ionic compound always have the highest boiling point. Here we have helium. Helium is noble gas atom there. So what matters really is that you look at the types of interactions there. Ionic compound, no problem. The increasing boiling point, calcium chloride, that will always be the highest one. Helium, if you look at the atomic mass for helium, 4 grams per mole. Okay, so helium is going to be the one with the lowest boiling point. But what happens to propane and methanol? Propane and ethanol. If you look at the molar mass, carbon-3, hydrogen-8, roughly about 44 grams per mole. Carbon-2, hydrogen-6, oxygen-1, roughly about 46 grams per mole. Similar in molar mass. Which one is going to have higher boiling point? Well, you got to write out the Lewis structure. Versus the key difference in this molecule. This is roughly around 46 grams per mole. This is roughly around 44 grams per mole. You add everything together. Carbon atom, oxygen, hydrogen, and oxygen there. So these two molecules are about the same size, but ethanol has a much higher boiling point because of hydrogen bonding.